Hey, this is Mr. Weiser. We're talking about the mechanical waves and sound summative assessment. So good work on this chapter. Let's finish strong. Number 1, the problem explores the general characteristics of a periodic wave. Figure P11 shows a wave produced on a taut string by a 50 hertz generator. What is the amplitude of the wave? So we've talked about the amplitude being from the 0 here to the highest point of a peak. So the amplitude is not from peak to peak, it's from the 0 level to the peak. So the amplitude is 2 millimeters. So that's A from the graph. Then the frequency of the wave, if we are getting this wave being produced by a 50 hertz generator, then that's our frequency. Our frequency is 50 hertz. That's frequency 50 hertz, 50 cycles per second. Nothing tricky about that. Then C, what is the wavelength? So the wavelength points on the wave that are going in the same direction or moving at the same pattern. So if I've got something here, the wave is going down, and something here, then it looks like the wavelength is 100 minus 20. So in this case, 80 centimeters is my units. So that's my wavelength. Distance between parts of the wave that are doing the same thing, 80 centimeters. And that should hold as well from this peak here to that peak is 80. So just to double check. D, what is the speed of the wave? The velocity of a wave is given by the frequency times the wavelength of the wave. In this case, the frequency is 50 hertz, 50 cycles per second. And the wavelength, let's just convert that wavelength to meters. So 80 centimeters is 0.8 meters. So you divide by 100, so 0.8 meters. That's it's going to be 40 meters per second. Last question, part E. What is the wave's period? So the period, T, we call it, is 1 over the frequency. So that means that if the frequency is 50 hertz, 1 over 50 hertz is basically there's a calculator right there. Okay, so it's like 0.2 or 0.02. I just don't want to get it. I want to get it right. So 1 divided by 50 equals 0.02. So 0.02 seconds per cycle. Remember, frequency is cycles per second, so 0.02 seconds is my period. And I just like to put seconds per cycle to help me remember. Okay, next question. You've got two waves moving. Let me get a different color here. You've got two waves moving in opposite directions. This wave is moving to the right, and this wave is moving to the left. And they're moving 5 meters per second. So the velocity equals 5 meters per second. They're headed towards each other. Draw the result. Okay, so artistically, draw the resultant disturbance 2 seconds later. So first question I ask is, how far does this wave go in 2 seconds? So distance equals velocity times time. So in 2 seconds, a wave that's going 5 meters per second will go 10 meters. So distance equals velocity times time. So if I've got something going 5 meters per second and I'm 2 seconds, then I'm going to go 10 meters. Seconds cancel. So basically, the center of this wave at plus 10, the center of this wave at minus 10, they're going to be right on top of each other in So that's one wave. Let's draw a different color for the different wave. In 2 seconds, they're going to be right on top of each other. And what happens when two waves that are look exactly the same, just opposite in amplitude, is that wave in 2 seconds is going to be completely flat. So here's the string, and then let's draw on top what the wave looks like. So maybe I'll use like a big old marker or something. So let's use a big old brown marker. So here's the string coming along. In 2 seconds, it's called destructive interference. So it will look like there is nothing going on that wave. So if this is 0 and this is -10 and this is 10, the string is totally flat in 2 seconds. I'll give you a little extra credit if you want to draw them like right before they combined, like at 1.9 seconds after, so 1.9 seconds after this point, but you've got to do a little bit of thinking about how they start kind of canceling each other out for that one. So that was after 2 seconds, and then how about after another 2 seconds? Let me get back to green here. So in another 2 seconds, what has happened? Well, we think, and we've seen, that this wave in another 2 seconds goes another 10 meters. So that one is basically going to be here. Nothing's been diminished. It's exactly the same wave. Remember, they pass through each other on a string. And we think that this one is going to be right here. So this is t plus 2 seconds. Got to sneeze, sorry. And then t plus 4 seconds. So time t right now, t plus 2 seconds, to use kind of a rocket thing. So let me draw this then. All right. Get my big, thick brown here. So the one that is below is right here, cruising along. And then this is like the 0 point. And then the one that's above is right here, cruising along. And I'll label these points here. So this we think is -10. This wave is going this way. And we think that this is +10. And this wave is going that way. And they are undiminished from their original shape. And they just keep cruising. Okay, next question. 124. We send a wave down a string. It reflects off a wall, which is 4 meters away. So let's put that over here. So we are from the generator of the wave to the wall. We are 4 meters. Notice that the wave is pinned here, so we're a standard pinned wave. And if the oscillation is small amplitude here, then we can assume that this is also a pinned section. So this is what a standing wave looks like on a string with fixed ends. And we have then waves going in opposite directions that are constructively and destructively interfering in this way. So first question, how many nodes and how many antinodes? So the nodes are where the amplitude of the wave appears to be 0. So we've got 1 node, 2 nodes, 3 nodes, 4 nodes, and 5 nodes. So that's 5. Remember, this amplitude is considered 0 because it's pinned and it's moving at a small amplitude. And then antinodes are where, I could do it in a different color. Antinodes are where things are very exciting. So maximum amplitude. So 1, 2, 3, 4. 4 antinodes. What is the wavelength of the wave produced by the generator? So we know in a string that is pinned at 2 ends, we know that the wavelength is, or the length of the string is some number of half wavelengths. And indeed we see that this is 4 half wavelengths. So we have n equals 4 in this case, which means that L equals 2 times the wavelength. So that means that the wavelength equals L over 2. L is 4 meters, so that means that the wavelength is 2 meters. And that makes sense because we know that this is a complete wavelength of the traveling wave that's on this string, which is half of that, which is 2 meters, so it's a double check. C. What is the frequency of the generator? So, we know that F velocity equals the frequency times lambda. We know that the length is that. We know the lambda is that. The frequency. We know that the wavelength that these waves travel. Sorry, my phone was ringing. We know that the velocity of the wave is given to be 2 meters per second. We know that the frequency is given by this equation, and we know that the wavelength we just found is 2 meters. So therefore, the velocity divided by the wavelength equals the frequency, which equals 2 meters per second divided by 2 meters. So that is, the frequency is 1 hertz, or 1.0 hertz. So I couldn't remember which question I told you was going to be on the final, which one was homework, so I'll just do both. You pick which one, you can remind me. So here we go. Number 134, we'll do that one first. So you've got a flute. A flute with all its holes covered, we imagine to be a tube with open ends. So we draw that like this. Neither end is closed. And then what happens with the pressure in a flute? So the pressure is a max at the ends, or it's atmospheric. So the wave that winds up being generated in a flute looks like this. This is like the pressure. That's like the pressure distribution or function inside the tube. And so what we know is that if the tube is L long, that we know that the wavelength of the wave is actually twice the length. In other words, only a half a wavelength fits in the tube. Alright, so assuming the room temperature is 20 degrees C, and you should know, I'm sorry, let me put that down now. Can you hear me? Sorry about that. So the tube has open ends, and this is the description. This is a half a wavelength. These are each quarters, so the wavelength is 2L, or 1/2 of a wavelength fits in the whole tube. You should know that the velocity of sound in air at 20 degrees C is 343.5 meters per second. Speed of sound in air at 20 degrees C. So if we're asking how long the flute should be, we're really asking what the L should be. We know that the velocity of sound in air is frequency times wavelength. We know that the frequency here is 262. So how long should the flute be from embouchure to end? So velocity equals frequency times wavelength. Wavelength equals 2 times L. Velocity equals F times 2 times L from this equation. L equals V over 2F. Solving that equation using algebra. We know the speed is 343.5 meters per second. We know that the frequency was 262 hertz. So if I do that calculation, I get that the length of the tube should be 0.65553 meters, or 65.5 centimeters. So that's question 134. Question 128. Let me scroll down a little bit. There we go. A narrow glass tube, question 128, is held below a loudspeaker and it's 0.5 meters long. Sealed at the bottom means we draw it like this. The sound, or the pressure distribution in a closed tube, there's kind of very high pressure at the bottom, and there's zero pressure at the top. Oh, so wait, hang on. The displacement of the molecules at the bottom is very small because it's a closed tube. The displacement of the air molecules at the top is very large because it's open to the atmosphere, a lot of room. The pressure goes the other way, so the pressure is very high. And then anyway, the length of the tube is 1/4 of a wavelength, because this can go out here to be a half a wavelength, and then of course it has to go a whole nother wavelength here to be a whole wavelength. So 1/4, so 1/2, 3/4, 1 whole wavelength. We know that velocity equals frequency times wavelength. We know that 4 times L equals the wavelength. So we know that the speed of sound in the room is the frequency times 4 times L, basically combining these two equations. So we get the velocity of sound in the room is the frequency, 170 hertz. Remember, that's the fundamental, so this is the fundamental mode. Other modes still have to be open at the top, but can be more wavelengths inside the tube. And 4, and times the length of the tube, 0.5 meters. So this is basically 340 meters per second, because 0.5 times 4 is 2, times 170 is 340. Let me just double check that answer here. Okay, so 340 meters per second. The last question is extra credit. Give it a try. And thanks for listening.